you set up, let me introduce you. So Franz is a PhD student here at TUE. He's with the Information and Communication Theory Lab, and he's working on various aspects related to radars and radar and communication. And today is going to be talking to us about OTFS. So can you share your slides? Can we do a co-host?
Yes.
Okay.
Can you see? Can you see the slides?
Yes.
Yes. Yes.
Okay.
Yes.
Yeah. So today I'm going to talk about OTFS radars and something which connects the two concepts, which is the Zak transform. And I'm actually very happy that there are some people participating in this workshop, like Robert Heath, and I don't know if Kaira is still here, because they also co-authored some papers on OTFS, and I'm kind of curious to hear their opinion or about my work. And so to get started, I was in a project with NXP looking into FMCW radars and communication, but at one point I also came across this OTFS waveform. And in this talk, as I mentioned before, I'm going also to talk about radar. And there's, I would say there's an intersecting part, which is the Zak transform, which can be used to describe both. So you can see that OTFS and radar, like a communication waveform and the radar waveform, do not have to be something different. And I'm not going to talk about very much in detail about OTFS. I will mostly focus on different aspects, or like how this connects, and I will jump between those three concepts during this talk, and in the end I will boil them down, and you can see that this nicely connects using this Zak transform. So so OTFS was like introduced like already something like 5 years ago. And the fundamental concept of OTFS is that it places symbols, information-bearing symbols, in the delay-Doppler domain. Like OFDM places symbols in the time frequency domain, OTFS places them in the delay-Doppler domain. And when is this useful? This is useful when you talk about channels with high mobilities, like you have certain reflectors or the receiver and transmitters are moving. And so that the received signal in such scenarios is a superposition of delayed and Doppler shifted replicas of your transmitted signal. And the big advantage of OTFS is that it turns a time variant channel, which would be experienced in OFDM, into a time invariant channel. So this means that all symbols placed in the delayed Doppler domain experience the same channel. So for example, in this case, here we have some symbols placed in the delay Doppler domain. The channel interaction is then a two-dimensional convolution, and the receiver will see this inter-symbol interference in the delay Doppler domain. So unlike what is here presented in this delay Doppler domain here, that there are only few symbols defined, usually you define the entire grid, and you will see that there is a lot of inter-symbol interference in the delay Doppler domain at the receiver. And usually you do some message passing algorithms to do the symbol detection. But this is not the point of my talk today. I will talk about more on the signal perspective of OTFS. So how is OTFS typically described? So in OTFS, typically you define the symbols in the delay Doppler domain. Then you apply a so-called inverse symplectic finite Fourier transform. This is a two-dimensional Fourier transform which maps the symbols defined in the delay Doppler domain to the time frequency domain. The symbols in the time frequency domain are then mapped to the time domain using this Heisenberg transform. The Heisenberg transform in this case is simply OFDM modulation. And after that, the symbols, the signal is sent over an time frequency dispersive channel, which introduces delay and Doppler shifts. And at the receiver, you do the inverse operation from the Heisenberg transform, like OFDM demodulation. And then you map the symbols in the delay Doppler domain back to the time from the time frequency domain back to the delay-Doppler domain. And let's look into details. What is this symplectic finite Fourier transform and the Heisenberg transform look like? The inverse symplectic finite Fourier transform is basically a two-dimensional Fourier transform. The term symplectic stems from the fact that we have two different signs here in the Fourier transform. One is a inverse Fourier transform, while the other one is a Fourier transform. And what is it doing is that when we define symbols in the delay-Doppler domain, so this is a grid in the delay-Doppler domain, we have L samples in the delay domain, we have K samples in the Doppler domain, is that it maps these symbols to some symbols in the time frequency domain. And you can see that's a two-dimensional waveform Fourier transform. So if you define one symbol here, it gives you a wave in this domain, where you can have certain orientations of this wave and frequencies. And what is also happening is that it changes the dimensionality. What was first the delay domain. So here we have L samples in the delay domain. We get then L subcarriers. And what was here the K samples in the Doppler domain, they will become M symbols in the time domain. And in the end, what we're doing is we map the symbols using standard OFDM transmitter processing onto a time domain signal. So we have here, when we look at the inner sum, we have here the subcarriers, like with subspace spacing delta F, and which is typically chosen to be the inverse of the pulse length, capital D. And that's everything at the moment what I'm going to talk about OFDS. I will come later back to this OTFS, but let's continue and let's talk about some radars. So there are many different types of radars, like you have these continuous wave radars, and another type of radar is this pulse radar. When you look, for example, in this radar handbook by Skolnick, you can see that the pulse radar is defined by this radar which sends repetitively rectangular pulses. And how does this look like? Suppose we have here a radar, a stationary radar. We have a moving target at a certain distance r and with a certain velocity v. As I said before, the radar transmits a pulse train of k pulses, where each pulse has a length of capital D. And between two pulses, we have this pulse repetition interval. How does the received signal then look like? We have some attenuation, then we have a delay, and we have some Doppler shift, which are indicated here by this dashed line. So typically, what you assume in radar is that the pulse, the distance between the pulse repetition interval is so short that the target movement between two consecutive pulses can be neglected. If this would be chosen too long, you have phenomena like range migration. And a second very important assumption is that the pulse itself is so narrow that you can neglect the Doppler shift of this pulse. And what we can see, or we assume further, that there's only a constant phase. The Doppler shift influences only the phase of this pulse, but this phase changes between two consecutive pulses. At the receiver, we do not process the analog waveform. Instead, we sample the received signal. So here in this case, we collect L samples between two consecutive pulses, and the processing is done in the discrete domain. And how does this look like, this processing? What you do is you arrange your samples in a two-dimensional grid. So what you do is, like, you take the first sample and then the next sample spaced by L and so on, and arrange them in a column here. Then you go on, you take the second sample and arrange them here in the second column, and so on. For example, in this case now here was the target present. So we can see here the pulse being present at a certain range pin, and each of those samples will have a certain phase rotation. And the Doppler processing is then done by taking the discrete Fourier transform along the columns of this range Doppler matrix. And this, since this is a modulated signal now, the Fourier transform will compress the spread signal into one impulse. And what we can see then here, we have the range Doppler map, and we can identify the range and the Doppler shift of this signal, which gives us the range and velocity information of the target. So now let's go already to the Zak transform. So the Zak transform is a signal transform. It has been, the origin is from in quantum physics, but there has been also it's quite useful also in signal processing. It has been used in Weyl-Heisenberg frames and other applications. And when you look at the Zak transform, it's just defined as the discrete Fourier transform of a subsampled sequence. So here we can, the summation is over L. So we can see here a subsampled sequence here. And what is also happening is that we have the subsampled sequence, we start at a different starting index. And when we look how this is computed, it's nothing else than when we arrange our samples in a two-dimensional, or like in this matrix. So we take the first L samples in the first row, the second L samples in the second row, and so on. And we can calculate the Zak transform by taking the Fourier transform along the columns. And this is exactly what we were doing before when we talked about the pulsed radar, the receiver. We exactly did the same. We arranged the samples in this matrix, and we took the Fourier transform along the columns of this matrix. So we can say from that perspective, the radar receiver applies the Zak transform. So the Zak transform has some interesting properties. Since we're talking here about discrete signals, and we're talking about or finite length discrete sequences, we can like what we do in standard DFT processing, we can also consider them to be periodic with period n. So when you take now consider the sequence to be periodic with period n, we can also introduce some properties in the Zak domain. So first of all, the Zak transform is quasi-periodic in time. What does this mean is that when we look at a shifted version of the Zak transform, like we look at the different indexes where the index is spaced by capital L, we see that this Zak transform is equivalent to the Zak transform at the distance at n, but we will get an additional complex factor here. And moreover, it's periodic in frequency. Those two properties are quite intuitive when you think, for example, here, since it is the Fourier transform, the discrete Fourier transform, and the discrete Fourier transform is itself periodic in the frequency domain, this will give you this property. And here we look at shifted version of the subsampled sequence, and a shift in the time corresponds to a linear phase in the frequency domain, which gives you this property. This can also be nicely visualized when you talk about here this properties. So we're talking about periodic sequences, and here we talk about this here we talk about this fundamental rectangle. As I said before, it extends quasi-periodically in time. So here in the x-axis, we have the index n, and in the y-axis, we have the index k. And what I missed before, because there was a jump in the slides, I'm sorry for that. We always have the constraint that k and l, which we choose here, the parameters, they have to be equal to the length of the sequence or the period of the sequence, because this guarantees that we always can arrange the sequence in such a matrix. And what the point is here, that is, we can fully describe a periodic sequence by only looking at this fundamental rectangle here. we do not need the values here because they are just a replica of these values here, which is also quite logic because we have a sequence which is of length n, and here we have n samples. So we just need to know this n samples and we can fully describe this sequence. And there's also, of course, the inverse relation. So we can calculate from the Zak representation of a signal, also the signal itself. And this is done via this sum relation. So what we need to do is we only need to sum along the k index of this Zak representation. And if we use this quasi-periodicity property, we simply can express the sequence like this in this form here, because we use the quasi-periodicity, we simply can write it as this. And this can be actually computed quite easy, so it might look a bit complicated here, but it's quite intuitive and to look at this. So we saw that the Zak transform was taking the Fourier transform of a subsample sequence. So we can say now the inverse Zak transform is reversing this operation. So first of all, we take the inverse Fourier transform of the columns of this matrix, and we get a sequence. And then what we're doing is we upsample this sequence. So we get a space, like we get a train of impulses. Because, for example, in this example, here I define the index k equals 0, which gives me a DC component. And then we spread the symbols here. And here the gray dots are 0 values, so they don't give us any value. For example, here we get a 0 sequence, and they again are spread over here. And since this is the starting index n, we start here at like starting index 1. And we start here spreading them with index 1, and so on. And then we get here, our full sequence is then this. This is just a train of these pulses, which are, each of them is spaced by capital L. So we can also define different points here in the Zak domain. For example, if we define here now a point which is at the k equals unequals to 0, this will give us then a modulated signal. So for example, here the blue indicates the real part of the sequence, and the red indicates the imaginary part. And this sequence is then also again spread. We see here the starting index is 2, because 0, 1, 2. We start here at 2, and we start spreading the sequence. And the interesting bit here is that all of those points are actually, all of those sequences which can be recovered from single points here are orthonormal sequence. So we have actually that the Zak transform is an orthonormal basis. And now how does this, two more properties I would like to talk here, which is also, when you talk about OFDM, you have circular convolutions, and which turns into multiplication in the frequency domain. But in the Zak domain, when we have a circular convolution of two periodic sequences, they turn into a convolution in the Zak domain of the two sequences with respect to the variable n. So we convolve along the time index. If we have a modulation, it means the element-wise product between two sequences. What we get is that we get a convolution with respect to the frequency variable in the Zak domain. So we can calculate the Zak domain representation of the modulated signal by just convolving the Zak domain representation from the individual signals with respect to k and l. And how does this relate to radar? So far we have seen that we can describe the radar receiver with the discrete Zak transform, but the question is now, can we also describe the transmitter with the Zak transform? And the answer to this is yes. As I showed you before, a single non-zero element in this fundamental rectangle, when it's located at location n0 and k0, which is indicated here, will translate to a pulse train like this, which is spaced. And when we map this sequence onto analog waveform using pulse amplitude modulation, we can see that we exactly get our radar waveform, which I was presenting before, where here LD is equal to the pulse repetition interval. And now, before turning the attention to OTFS, I would like to address some point regarding OFDM, because so far, or in most of the majority of the papers on OFDM, you use on the papers on OTFS, you use OFDM in the end. So you do this symplectic Fourier transforms to get the time frequency domain representation of the signal, and then you do an OFDM transform. But the OFDM transmission usually represented by this analog modulation here. You have your symbols defined in the frequency domain, which you map onto a modulated pulse, where the pulse length is this capital D, which relates to the subcarrier spacing. But in reality, that's not how OFDM is done. So the great success of OFDM actually came or is due to its digital implementation and fast Fourier algorithms. And what you're doing is that you have actually, we replace this pulse G of D by shorter pulses. And what you can get, how the implementation looks like is this way. So you have the symbols in the frequency domain, you perform an inverse discrete Fourier transform, you get your sequence. And to sustain the cyclic properties, you add a cyclic prefix by copy pasting the last L symbols, or like the length of the cyclic prefix. And then you send this and do pulse amplitude modulation, which can, like this can model, for example, the low pass filter. And when we talk now about OTFS, we can also talk about the digital implementation of OTFS. And when we talk about this, we can talk about, or I showed you already that we can represent the symbols in a matrix form. So we have our symbols in the delay-Doppler domain, which are a matrix of size k times L. And also when we do the symplectic finite Fourier transform, we can get a matrix which represents the symbols in the time frequency domain. And with a slight abuse of notation here, I'm using also this small x to represent this matrix of the time domain signal. So where we have in the rows the L samples, like the first L samples are in the first row and so on. When we use this notation, we can see that the inverse symplectic finite Fourier transform is nothing else than applying a inverse Fourier transform to the left of this matrix X in the delay-Doppler domain and Fourier transform to the right of the matrix X. And the OTFS modulation, or the OFDM modulation here in this case, would then be applying, the inverse Fourier transform to the right of this matrix. But this just, then we have, if we use this relation here, we get here a unit matrix and it ends up to be like this. And this is actually nothing else what I presented you before, taking the Fourier transform along the columns, or the inverse Fourier transform along the columns, and we get then our matrix here. So from that perspective, we can see that the inverse symplectic finite Fourier transform plus the OFDM modulation resembles the inverse discrete Zak transform. And when we talk, then we can also model our OTFS modulation in that way by saying, okay, instead of doing this way of modulating or transforming all the symbols from the delay-Doppler domain to the time frequency domain, we can directly apply the inverse discrete Zak transform on our matrix X in the delay-Doppler domain. We get a sequence in the time domain, and similar to OFDM, we want to have cyclic properties, so we add a cyclic prefix. And then we do the parallel to serial conversion, and we transmit the pulse amplitude modulation, and we transmit the signal. So I told you before that in OTFS, or like we are dealing with channels which introduce delay and modulation, or like Doppler shifts. So how does this look, this channel effects actually look like in the Zak domain or in the delay-Doppler domain then? And therefore we just that's actually something you can work out nicely graphically. So for example, we have here the matrix X, which represents the symbols in the delay-Doppler domain. When we apply the inverse discrete Zak transform, we get the samples in the time domain, which are arranged like described before. And this matrix is now here to the left. And we suppose we make a cyclic shift of this sequence by 1. What is happening is that the first sample gets to the second position, which you can see here. The last sample falls out of this row and comes in the next row. So X5, which was here, goes now here, and so on. And the last sample here, the X29, which was here, due to the cyclic extension, comes in at the first position. So when we do now the Zak transform on this signal is, again, taking the Fourier transform along the columns of this matrix. So what we can see is actually all the symbols which were previously defined in the first row are now in the second row, and so on. But since we have here in the first row is the previous last row, and this is nothing else than a cyclic shifted sequence itself. And since we're taking the Fourier transform here, we can see that we get, due to the cyclic shift property of the Fourier transform, is that we can see here we get an additional linear factor, this here, which are indicated here by these colors. So delay just shifts, cyclic shifts in the delay-Doppler domain, plus those which falls out in the back come in at the beginning, and they will get an additional phase. And for modulation, I didn't work out the graphical way, but you can also do it in a math way, very simple. So by using this modulation property. For example, when you have a delay modulation, Doppler shift, we can model this by this complex exponential here. And let's call this U of n. By looking at this U of n, the Zak transform of this U of n, we can see that this is nothing else a delta function with some additional complex factor. And when we use the modulation transform pair, that was that the Zak transform of two modulated signal is the convolution of the individual Zak transforms with respect to the frequency variable. We can see that modulation simply translates the original defined sequence or the Zak domain representation in the frequency domain. So from that perspective, or now so far we have described OTFS and radar, and we could nicely combine both of those ideas with using this Zak representation. So how is, for example, this used in OTFS itself? For example, when you do channel estimation in OTFS, you want to identify what is the delay and the Doppler shift introduced by the reflectors in the channel, because they cause the intersymbol interference. And what you want to do is, or what is done or proposed is that you place a pilot symbol in here and you keep some guard band around this pilot, because this allows you to directly observe how the symbol is delayed and Doppler shifted in this guard. And here you keep a guard band also before, because there's a maximum delay. For example, all those symbols will also spread into this guard band, and we don't want to get confused how this one is spread. Same here, because we have Doppler shifts, and Doppler shifts can be either positive or negative. We also have to keep a guard band up and down. And then we directly can observe, for example, in this case, this symbol can only be spread in this. So by channel estimating, actually, the OTFS is probing the channel like a radar is doing, a pulse radar is doing. The big difference is now in radar, you only define one non-zero symbol here, and you want to directly observe how the symbol is spread. Whereas in OTFS, you define the whole grid to carry information and just keep one small part empty. And also a big difference between OTFS and OFDM and pulse radar is that the choice of parameter. For example, when you talk about long-range radar in automotive application, you talk about bandwidths of 250 megahertz, whereas in 802.11b or something like that, you talk about 10 megahertz. So the range resolution is very different. And that's why, for example, in OTFS, you only expect small shifts here, and you contain actually the spread of the symbols in a small region. Whereas in radars, actually, you want to use this entire grid to see the spread and determine where some reflectors are, because they give you the range and Doppler information. And to conclude my talk is, I hope to give you a different point of view, because I think this Zak transform idea, it's very intuitive, it gives you a good understanding. And from the perspective, OTFS is nothing else than a pulse radar, which actually uses the whole delay-Doppler domain to define a signal, whereas a radar can also be considered as an OTFS system, which defines only one symbol in the delay-Doppler domain. And with that, I conclude my talk.
Thank you, Franz, for this very nice talk, which is also some sort of tutorial as well. I think Giuseppe has a question, so yeah, maybe we should.
Yeah, just a quick question on your last remark. It is true that when you want to estimate the channel and you have this pilot scheme that leaves a blank window with a single pilot, you are limited by, of course, the size of that guard interval. But when you want to use the whole digitally modulated OTFS signal to estimate a radar parameter, the fact that you have zeros or you have known symbols is exactly the same, apart from the complexity. If you can afford the complexity, you can still use the whole frame, and then you have exactly the same resolution in terms of Doppler and the range that depends on the size of the whole big frame, not only the pilot thing.
Yes, but what I wanted to say here is, for example, when you talk about automotive radars, you go to 77 gigahertz because the Doppler shift scales with the carrier frequency, whereas, for example, 802.11b is below 6 gigahertz. So there's still the parameter setting is a bit different.
Sure.
So from the physical resolutions perspective, they are different.
Yeah.
But I agree that you could also, like, there was also a paper proposed where they use this OTFS. They do, because you can predict if there's a target at a certain range and a certain Doppler shift, you can predict how the symbols look like. And then you can set up a matched filter and shift over this delay-Doppler domain. And if they match, you know that there's a target.
Yeah, it's mainly a matter of complexity. If you can afford the complexity and you can do maximum likelihood on the whole frame with all known symbols, then this is the same. As long as the duration and the bandwidth are the same, you can even see from the Kramer-Rao bound that the properties of parameter estimations are almost identical. We have done, Kramer-Rao bound with OTFS of OFDM and chirp, these compressed waveforms. As long as the duration, or you integrate of a certain duration, right, and the bandwidth are the same, the Kramer-Rao band are almost invariant on the waveform. So it seems that as long as the waveform is, say, random enough and spans certain duration and bandwidth, they behave essentially the same. Of course, this is true when all the symbols are known. Like, so when the receiver, the radar receiver is somehow aware of the signal that was transmitted. And of course, the complexity in doing the detection is completely different. If you have a chirp, you can do it in a very simple way and get almost maximum likely performances. If you have a digitally modulated signal, is a totally different story.
Yes.
All right. So thank you. Thanks again, Franz.